Business analysts claim that predictive maintenance has the potential to generate up to $11 trillion a year by 2025. How can that be? What is the story behind these figures? And what are the challenges ahead? Let me give you some insight. My name is Marielle Stulinga and I'm a professor at the University of Twente and Radboud University, the Netherlands. Maintenance is something that we do every day, both personally and professionally. We bring our cars to the garage for checkups and repairs. We floss and brush our teeth on a daily basis. And rail is regularly inspected for defects. Maintenance is an integral part of plant operations. So on the one hand, maintenance is crucial to keep systems operational and prevent failures. We don't want to get stuck on the road because of a car failure. We don't want chemical substance to leak because of a pump failures. But at the same time, maintenance is expensive and inconvenient. I'm never excited to see my garage or dentist bills. And moreover, if rail is under maintenance, then trains cannot ride and people cannot travel. So the question is, can we do better? And that is exactly the goal of predictive maintenance. So the central idea in predictive maintenance is to predict failures better via data analytics. The holy grail is maintenance just in time, exactly when and where it's needed. So how does it all work? We start by collecting data about the health of our assets through sensors and historical failure databases. Then, data processing techniques transform these raw data into meaningful information. We select the features we need, validate their integrity, and clean the data to obtain high quality and correct information. Step 3 concerns prognostics. Data analytic techniques prognose future failures via machine learning and artificial intelligence, as well as physical models. We predict relevant performance indicators, such as the number of failures, the remaining useful lifetime, and reliability. These prognostics are then used in the logistic planning. Knowing when components will fail is one thing, devising an effective maintenance planning is another thing. One needs to schedule personnel, equipment, spare parts, and this affects the entire supply chain. Moreover, it's not effective to stop production 1 week to replace the oil and the next week to clean the filters. Instead, we want to cluster maintenance actions. And last but not least, we need to consider human and organizational factors. In the end, maintenance solutions must work for people and organization. So both need to embrace this new data-driven way of working. Let me give you a short example. Before a gearbox fails, it will generate all kinds of observable behaviors. It will produce sound, vibration, heat, etc. And these can be detected via condition monitoring by using appropriate acoustic and vibration sensors. Data analytic techniques can then detect anomalies and determine the degradation levels. And such techniques form the heart of predictive maintenance technologies. There's also challenges: which sensors to use, where to place them, and importantly, variations in the operational conditions. Temperature varies along the day and with the season. So for a wind turbine, 30 Celsius is disturbing in winter, but not in summer. And convincing data analysis techniques to handle such variations is challenging. But the question is predictive maintenance effective? Predictive maintenance is widely considered as a very promising technology. And McKinsey sees it as the most promising application of the Internet of Things, with expected cost savings of 63 billion a year and 50% downtime reductions. So that sounds great, of course. Less downtime at lower costs. That's what everybody likes. However, realizing these benefits is very challenging. And a study by PricewaterhouseCoopers shows that only 11% of all companies use predictive maintenance. Most companies instead are at maturity level 2, with many visual inspections and some instrument reading. The problem, according to PwC, is that predictive maintenance is currently not leveraged. Small-scale solutions exist for contexts that are well understood, but is not a holistic, overarching approach. And that's why I'm very excited to lead the PrimaVera consortium. PrimaVera is a large research project with a budget of €5 million funded by the Dutch Research Council and WHO. And our goal is to make predictive maintenance easier and more effective, and to fully realize its potential, better performance, higher availability at lower costs. And on board of the consortium, we have 6 knowledge institutes as well as 11 society organizations. And we cover expertise from the entire predictive maintenance workflow with sensor specialists, data scientists, and maintenance engineers, as well as psychologists and business experts. So let's look into the grand challenges that we want to tackle, as well as other people. First of all, we aim at scalable and accurate prognostics. Indeed, mispredicting failures can easily lead to more rather than fewer failures, and that defeats the whole purpose of predictive maintenance. So our aim is to scale up solutions to larger systems and making them less data hungry and applicable in a more diverse operational context. And to do so, as I'll explain later, we plan to combine data-driven with model-driven algorithms. Secondly, we aim to integrate the steps in the predictive maintenance workflow. As observed by Pricewaterhouse, we need a holistic approach. And indeed, choices you make in one step affect other steps in the workflow. For instance, the type of sensors you choose determine what you measure, and that determines what you can predict. So multi-level analysis can optimize each step in the predictive workflow itself, as well as across different steps. Third, we want to automate the workflow. Current approaches require a lot of manual work in data cleaning, in configuring the data analytic approaches, and automating these will make them faster and easily. Finally, human and organizational factors are important. Predictive maintenance requires a digital transformation in the organization, meaning that work processes and people have to adapt to a data-driven culture. And at the heart of this transformation lays trust in the predictive maintenance solutions, trust in the black box algorithms. And of course, a multidisciplinary approach is also key in realizing these challenges. So for the rest of the talk, I want to focus on one of the steps, namely prognostics, and go a little bit more into the technical details. There are 2 approaches to prognostics, model-driven and data-driven. So model-driven approaches use models to predict performance indicators, such as the remaining useful lifetime, the number of failures, availability, etc. Such models can be a physical model, a fault tree, a finite element model, etc. And the good thing about such models is that they are white box, so they are understandable and explainable. On the downside, creating such models requires expertise. And for good predictions, you also need to know the operational conditions exactly. The second approach is data-driven. These are fast and need less domain knowledge. However, they do require a large amount of high-quality data. And moreover, algorithms are black boxes. So such models don't give any insight why a system fails or why it degrades. And this is largely because current technology is very good at finding correlations between failures, but not in finding causations. And lack of understanding can affect the trust in prognostic algorithms. And we want to reconcile the model-driven and data-driven approaches. And this aligns well to the smart industry roadmaps, which states that the challenge is to reconcile the perspective of the domain experts with their failure modes and the data analysts with the correlation. And our aim is to get the best of both worlds. A model-driven approaches include physical models like finite element models, differential equations, and fault trees. So these models have proven their success, and they're largely from the 50s. Data analytic approaches include neural networks, Bayesian networks, etc. And what many people don't know is that they're also from the 50s. And it's the recent emerge of data storage and computation power that makes those techniques work in practice. And to combine the data-driven and model-driven approaches, we can go in either of two directions: model to data and data to model. And in the first directions, models help data analytic techniques. And there's a few ways to do so. Accelerated learning, where you pre-configure your data analytics and algorithms with the help of a model. Alternatively, a data augmentation use a model to generate additional data in case of missing or incorrect values. Models can also be used in data validation, where models can check if the data is correct or not. And models can then help in data cleaning by removing or correcting data that does not conform to your model. This is again very novel and active research in progress. Then in the other direction, we use data to improve our models. And again, there's several ways to do this. First of all, and rather classic, is parameter fitting, where you use data to learn the parameters in your model. For instance, the exact load or the exact operational conditions. You can also learn the optimal setting of the parameters, so the optimal load under which your system performs best. I will tell a little bit more on learning the model itself. So you can construct parts of a formula or the formula itself via data analytic techniques. And this is an example where we combine model and data in the analysis of the electrically insulated railroad joint. You see here a fault tree model that summarizes all failure modes in the model. And we have used data analytics to predict the unreliability as well as the maintenance costs. So the left graph shows that if you never do any inspections, then your unreliability is very high. And that is the black line. But the more inspections you do, the lower the unreliability. The graph on the right gives insight in the maintenance costs. So how do costs increase or decrease with the number of inspections? So black is the total costs broken down in inspection costs in green, preventive and corrective costs in green, and failure costs in red. And we observe that if you never do any inspections, all the costs are very high. But as soon as you do inspections, your total costs decrease. And at some point in time, it doesn't matter anymore because the costs stay flat. Now, learning fault trees from data. Classically, what you do, a fault tree gives you a risk prediction for the numbers of failures or the availability. But what we have done instead is to learn automatically a fault tree model from data. So given the data record of a system, given when components fail, can we then automatically derive our fault tree model? And we have been doing this with genetic algorithm, and we were indeed able to learn the fault tree automatically. And currently we're extending this to a trust bridge model as the one in this picture. And furthermore, we have used synthetic data in our studies. And that is a good first step, because then we have the data quality fully under our control. But an important next step is, of course, to do this for real-life data. What have we seen today? Well, I've tried to convince you that predictive maintenance is a promising technique, but it's hard to realize its benefits in practice. So I've shown you two approaches for prognostics, namely data-driven and model-driven. And finally, I've shown you two ways to combine these by learning fault trees from data. So I want to end my presentation with some food for discussion, because a question that many people ask me is, where do I start when introducing predictive maintenance? Can you give me some do's and don'ts? So here they are. So what I see in a lot in companies is they have large amounts of data, but not the right quality or not of the right type. So the quality of a prognostic algorithm is of course as good as the data you can put in. And while data push is useful, I would advocate data pull, so that you first think what you want to measure and then think how to measure it. Secondly, I also advocate to hire data scientists. So predictive maintenance is very often carried out by mechanical engineers and maintenance engineers, and they have important knowledge on maintenance and failures modes, but not always an in-depth knowledge of data science. So these days there's many data science programs at universities, and employing their graduates would be useful. And finally, I think it's important to align stakeholders, because it's often the case that the department that implements predictive maintenance and makes the costs is not the department that reaps the benefits. So this includes traditional stakeholders, but also maintenance workers. And I'm curious to hear if you agree or not, and I'm happy to discuss these points with you.